Our electrical grid, it's this incredible, massive machine, one of the most complex ever built. But trying to upgrade it for the 21st century, that is a huge, huge challenge. So today, we're going to dig into a scientific paper that proposes a surprisingly simple and low-cost solution. And it uses the powerful communication network that most of us are carrying around in our pockets right now.
All right, so here's how we're going to break this down. First, we'll talk about the grid's big problem. Why is this so hard? Then we'll get into this really clever cellular solution. After that, we'll see how the researchers actually built a virtual power grid to prove it could work, what the data from that simulation showed, and finally, what it all means for the future of our power.
So we all hear about the smart grid, right? This idea of a grid that's way more efficient, way more reliable, and sustainable. It sounds fantastic. But there's this one giant roadblock that keeps stopping us, the massive cost and sheer complexity of building the communication network that makes it all work.
At the very core of any smart grid is something called the Advanced Metering Infrastructure, or AMI for short. Now, the easiest way to think about it is as the grid's central nervous system. It's the network that lets the utility company and all the homes on the grid have a two-way conversation in real time. The problem is, building that entire nervous system from the ground up is incredibly difficult.
The way we try to do it now is to build a whole new, dedicated data network. And it usually ends up being this mishmash of different technologies. You've got new fiber optic lines, wireless WiMAX towers, DSL, satellite links, you name it. The paper itself says that trying to mash all these technologies together is both costly and more complex. And that creates a huge barrier to getting this done on a wide scale.
So how do you get around a problem that massive? Well, what if you just didn't build a new network at all? And this is where the paper's solution gets really interesting. It just sidesteps that whole infrastructure problem by using a network that's already been built, is super robust, and, well, is pretty much everywhere.
Instead of building a new data highway, the idea is to just rent a lane on the superhighway that's already there, our cellular networks. The concept is that every single smart meter gets its own SIM card. It then communicates just like your cell phone, sending all that critical data, power usage, voltage, system health, directly to the utility's control center.
And this really shows you how simple it is. No new wires running to your house, no complex patchwork of different technologies. You just replace the old meters with new smart ones that have a little GSM module inside. And the best part? The maintenance of the communication network is handled by the telecom companies, not the utility.
But okay, that's a great idea in theory. How can you be sure it'll actually work in the real world without spending a fortune on a pilot project? Well, before you build it for real, you build a digital twin. You simulate the entire system inside a computer. And this is exactly what the researchers did. They used this powerful engineering software called MATLAB and a tool inside it called Simulink. You can almost think of Simulink like a set of digital Legos for engineers. It's a visual, drag-and-drop environment for modeling really complex systems. Using this, they built a complete virtual power grid from scratch, which let them test their cellular idea safely and really thoroughly, with absolutely no real-world risk. And this wasn't some simple little model. To make it feel like a real, modern grid, their simulation included a mix of power sources, a traditional diesel generator, but also renewables like a solar PV system and a wind turbine. They built out the entire electrical circuit with all the realistic components like transformers and loads. But, and this is the most critical part, they also modeled the entire cellular communication system and then built in ways to trigger virtual faults like power outages just to see how the whole network would react under pressure.
So let's zoom in on that communication part for a second. How does it actually work? How does the information about a power fault, for example, get from a virtual house all the way to the virtual utility control center? Let's follow the data's journey.
The key takeaway here is that the data follows the exact same process that your phone uses every day. First, all the different readings from the meter, voltage, current, power, get packed into a single digital box. That's called multiplexing. Then, that box gets placed on a specific cellular frequency, like a delivery truck getting on a specific highway. That's modulation. On the other end, the utility company takes the box off the truck. That's demodulation, and unpacks it to see all the original readings. That's demultiplexing. And what the simulation proved is that this standard process works perfectly for grid data.
Now for the most important test in the whole simulation, speed. If there's a fault on a power line, the utility needs to know about it instantly. So the researchers measured exactly how long it took for the system to detect a fault and clear it, and they tested it on different generations of cellular technology.
The results were really impressive. The simulation showed that even on an older 2G network, the system could detect and clear a fault in just 0.4 seconds. On 3G, that dropped to 0.3 seconds. And using a modern 4G network, a fault was cleared in just 0.2 seconds. This proved that the cellular approach isn't just feasible, it's incredibly fast and responsive.
So, the simulation proved the concept works beautifully in a virtual world. But what does all of this mean for upgrading the actual grid we all rely on every day? Let's zoom back out to that big picture.
This approach really presents a clear trade-off. On one hand, you get a much cheaper, faster, and more secure path to a smart grid, with 24/7 monitoring and maintenance handled by the telecom experts. But on the other hand, it requires massive logistical coordination. I mean, you'd have to replace every single meter. And it creates a new reliance on third-party cell companies, which would require some very complex business agreements.
Ultimately, this research provides a really compelling blueprint. It suggests that the key to unlocking a truly smart, responsive, and efficient 21st century power grid isn't some brand new, exotic technology we have to go out and build. Instead, it might just be the one that's already in the palm of our hands.